Hello everybody, this is Michaela Mooney and I am doing Vertex Edge Graph 6 discussion assignment. And today we are going to be using Kruskal's algorithm to find minimum spanning trees for graphs. Down here I went ahead and wrote out the definitions for minimum, spanning, and tree. Minimum means we're looking for the lowest total cost. Spanning means we're going to connect all the vertices to each other through a network. So that means they don't have to be, like D doesn't have to be touching every single, that was not an edge, but D doesn't have to be touching every single vertex. It just has to be connected through it through other vertices. So it can be going like that to get to C, or this way to get to F. It just has to be able to get to every vertex, even if it passes through other vertices. And then tree means there are no circuits. So that means we are not going to be starting and ending in the same place anywhere inside the network. And Kruskal's algorithm is guaranteed to give us a minimum spanning tree. And I went ahead and wrote down all of the steps that we need to take to get our minimum spanning tree using Kruskal's algorithm, and that is what we are going to do today. So let's go ahead and start with graph number 1 and step number 1, which is start with no edges being a part of the solution. And we have already done that. We haven't drawn or done anything on our graph, so step 1 is good. For step 2, we are going to add edges one at a time, starting with the cheapest edge. So let's go ahead and look for the cheapest edge on our graph. I see a couple of options. I see the ones. If we start with ones, there's two ones. There's 1.2 and 1.8. So we're going to go ahead and pick the edge that costs 1.2. And I'm going to highlight the vertices as we touch them, so that way we know we've touched them, because we need to connect all of the vertices to get to each other. And then we can go ahead and keep adding the next cheapest edge, which is 1.8. And it's okay that these edges aren't connected to each other yet. As long as we do along the way, then it's good. So we don't have to worry that they aren't touching yet. So now let's look for the next cheapest edge. And if we've done all the ones, so let's look at the twos. There's 2.9, 2.4, 2.2, and 2.3. So we can go ahead and add 2.2 because that's the next cheapest edge, and we add a new vertex to our network. But now here's where things get a little tricky. And let's look at step number 3 to help us. So step number 3 says, don't add an edge if it would create a circuit. And let's look at the next cheapest edge, which is 2.3. If we were to add 2.3, that would create a circuit between C, F, and B. So that means we cannot add it to our minimum spanning tree. So I'm going to cross it out. But step 4 says keep adding edges until every vertex is connected to the network. So let's just we'll skip 2.3 because it creates a circuit, and then we'll look at the next cheapest edge, which is 2.4. And that connects it connects all of the edges that we have highlighted so far. So we do have a network going on, which is good, but we still have one vertex to add. And we have the next cheapest edge is 2.9. So that is perfect because now we've used the lowest total cost. We started with the cheapest edge and went with every cheapest edge we could go that doesn't create a circuit. And we've connected all the vertices to each other through a network. So that means you can get to any other vertice through our network from any vertice, which is good. And we don't have any circuits because you can never start and end in the same spot without going over an edge more than once. So we have successfully used Kruskal's algorithm to find a minimum spanning tree for this graph. Let's move on to graph number 2. I rewrote the rules for us to help us as we go along. And so let's get started. So for step number 1, start with no edges being a part of the solution. Good, we've done that. On a roll. Number 2, add edges one at a time, starting with the cheapest edge. So let's go ahead and look for the cheapest edge. We have, if we start with the ones, I only see one, which is 1.8 right here. And again, I'm going to highlight vertices as we go so we know we've touched them. Next cheapest edge, if we look at the 2's, we have 2.1, 2.8, 2.7, 2.3, 2.9. So let's go ahead and add 2.1. And remember, it's okay that they aren't connected yet, because they will be eventually. And now, so we did 2.1. I don't see any 2.2's, but I see a 2.3, which connects our network, which is very good. And then we have 2.9, 2.7, or 2.8. So let's go ahead and add 2.7. And it's okay that it's not touching. We will connect it eventually. So after 2.7, we can go to 2.8. Very good. That connects our network. So that's very nice. But now, remember, step 3, don't add an edge if it would create a circuit. So our next lowest is 2.9 right here. But if we were to add it, that would create a circuit between H, C, and B. So we cannot add it to our network because we don't want any circuits. But we're going to keep adding edges, like it says in step 4, until every vertex is connected to the network. But there's not going to be any circuits. So after 2.9, our next lowest is 3. But look, this one's going to create a circuit too between A, B, and H. So we cannot add this one to our network either. But there's still more edges, so let's keep moving on. So after 3.0, we have 2 3's left. We have 3.9 and 3.5. 3.5 would be the next lowest edge, but look, this would also create a circuit between E, H, and F. So we're 0 for 3, and we cannot add 3.5 either. But no worries, our next lowest is 3.9, and look, it connects G to our network, and it doesn't create a circuit. So we have successfully made a minimum spanning tree because we used all the lowest edges we could. We've connected all the vertices to each other through a network, and we haven't created any circuits. So using Kruskal's algorithm, we have a minimum spanning tree for this graph. Yay! Now let's look at graph number 3. Same rules, same algorithm. Let's get into it. Starting with no edges being a part of the solution, we're going to add edges one at a time, starting with the cheapest edge, and we're not going to add an edge if it would create a circuit, but we're going to keep adding edges until every vertex is connected to the network. So we're looking for our cheapest edge, and I think the 20s are going to be our lowest to start with. And we have, I see 23, 21, 28, and 29. So 21 is going to be our lowest. And I also want to note that these are not vertices right here. Even though the edges cross and connect there, they aren't vertices. So we don't have to worry about them when we're connecting vertices to each other and edges are overlapping. But I just wanted to make that point, that these are not vertices, so we do not have to worry about them. Anyways, moving on to the next cheapest edge, which is going to be 23, and that connects B to A, which is very good. And then 28 also connects, and it's okay that they're all coming out of B because we haven't created any circuits, and we're connecting them. We're connecting all the vertices, and that's what we want to do. So after 28, our next cheapest edge is going to be 29. But look, that's going to create a circuit between A, B, and E. So what do? We skip it. We cross it out and we say, sorry, you can't be a part of our network. Our next cheapest edge, we're out of the 20s and into the 30s. And I see we have 30, 36, and 34. So 30 would be our next cheapest edge, but look, that's going to create a circuit too between A, D, and B. So it also cannot join our network party and has to be kicked out. We skip it over. Let's look at our next cheapest edge, which is going to be 34. That we can connect to. And remember, even though it's crossing through these two edges right here, and it looks like it's making a circuit, it's not, because these are not vertices. So this is okay that it's crossing through here. And it actually completes our network because it connected the last vertex we needed, and it doesn't create a circuit. So that means we have successfully used Kruskal's theorem to create a minimum spanning tree because we used all of the lowest vertices we could. We connected all the vertices to each other through a network. Even if you have to cross through vertices to get to another vertice, that's okay as long as you're able to reach all of the other vertices. And we have no circuits. So we did it. We've successfully done it to all three graphs. Thank you so much for being here with me and listening to me. I hope you learned something new, and I'll see you next time. Bye!